All right. So we have just like what I said I showed last time. Here are some actual pictures of some atoms. The top two are actual pictures with an actual camera, just a regular camera. So that's just like a device that is holding an atom together with some magnetic fields. And that one was, awful to try to see, so I made it bigger. You still can't really see it. I thought the projector would be a little bit fixed, but there is a dot. You guys want to see it later. There's a little fleck in there. Bottom left, that's an actual movie made from, I believe it's some sort of carbon atoms. IBM was sort of making a bunch of these for promotion. And this is an image of a hydrogen atom. This is just to show you guys. It's not really related to what we're doing. It's just pretty cool. All right. We're going to start. I guess I'll start with a couple of announcements. So I'm going to be assigning the first homework tonight. When I get home, I'll assign it, and it will be due next Thursday at midnight. So you got a week to do this homework assignment. It's just going to be on this first chapter, or this first topic. Let's get up to showing you what that is. So if you don't already have the homework service, you're going to go to Canvas. You're going to follow those steps that I've said. So there is a step to get signed up for WebAssign, so you can do the homework. So today we're going to talk about, I'm going to try to get through all of these today. We have units, trigonometry, and vectors. This is basically like a review chapter, trying to see if everyone is up to speed on units and maybe some trigonometry you've had before. If you've never had it before, this is a good place to learn for the first time. And then I think I'm just going to barely get to vectors. If I finish early, yeah.
Do you upload your PowerPoint?
Yeah, I do. I upload, so it's recording. It's going to be in a video.
Yeah, but do you upload them before lecture? Or?
No. Yeah, so I'm going to try to, get through up to vectors. If I've only prepared so much for today. It's sort of a test run to see how the pacing is going to go. So let's start with some units. SI units. You may have heard this around before if you've taken a chemistry class or a biology class, any sort of general science class, maybe in high school. These are sort of the main units we'll be using. And you might be thinking, why have we chosen these ones? Why have we chosen a meter, kilogram, and seconds? These are the ones that we're going to use. There's others for like electric current and for temperature, but these are the ones that we're going to see on like a daily basis. So we have length. So the units is what I have in the brackets, just the brackets. Okay. Now, why is a meter the SI unit of length? So SI, so that's just French for international standard. They've swapped the words, so it's SI, abbreviated SI. they, everyone all over the world had their own system of measurement, and it was a nightmare. For length right here, the meter, actually before we even get to the meter, let's pause on this. You don't have to write this down yet. So before we even get to a meter, why was that even chosen in the first place? We have here in the U.S. we have feet and miles still. These are imperial units. We get them from just a carryover from Britain, and they got it from other cultures like the Romans and Greeks, and it was basically just like some emperor, some king at the time could at any moment say, you know what, we're making all of the measurements of the town based around me. So here's my foot size. I'm a king, I'm royal, I am, divine. Make all the measurements around this. So, the foot has developed in its own way since then. It is still not the greatest way to do measurements. So, in the about 1850s, everyone was tired of going from town to town and saying, oh, I have this piece of wood or this board that I want to buy is so many feet long. And you can't really trust what they're saying because different towns have different people ruling them. And it's just a nightmare trying to, for a growing world, for people trying to mix together. It's, awful. So in the 1850s, there's a standardization happening. So we came up with the meter. And this is where we we're saying what's something that won't change? What's something that is like a true fact that we can stick to and it will stay, the same always? They came up with this idea to base a meter off of the length or the distance from the equator all the way to the North Pole. And they just said 10,000 kilometers. They just said that, and they said, okay, divide it out. We get to, okay, then 1 meter is about this long. And everyone agreed. They went about their own ways. But some people actually are curious about this. They want to make more precise machines, more precise things. They're using this meter, and they say, wait, your meter is about this long. Mine is just this long. It's not that much, but that is a severe difference if you're trying to make something that is small and intricate. So, in about the 60s, in the 1860s, when was it? No, it's the 1960s. They developed this sort of thing, this bar right here, and they actually went to every country. This is sort of a prototype. They went to every country and they said, here, this is 1 meter. Don't lose this. This is the standard for all of your measurements. And why is it platinum iridium? That's because if you're having this thing that's very precious to your own measurements, you don't want it to, bend or stretch. You guys know a little bit about metal is that if it gets a little warm in the room, metal might expand a little bit. If it gets cold in the room, the metal might contract just a little bit. Platinum iridium, it sort of resists that a bit, and it doesn't really rust. So you're able to have this thing in a room. It's in a room, it's in a vacuum chamber. There's a guard watching it, and that's the standard of measurement. You can also see how that is sort of tough to maintain. someone always taking care of this, just thing that is a standard. So I think it said 2019, so not even that long ago, they changed it. It was based off of this for a long time. 2019, they changed it to be just off of something even more precise. Maybe someone, didn't have that bar in a vacuum chamber and it sort of rusted away a little bit over that amount of time. Something else that's, just isn't going to change. We're trying to get more and more precise as we continue in the, better technology. We're using a sort of a system of measuring a meter on how far light will travel in a specific amount of time. So light will always be traveling at the same speed. So the light in this room bouncing off that sort of a thing there at the ceiling, light from the sun, all light travels at the same speed. And light travels at the fastest known speed possible. And now that we have very accurate instruments, we're able to very accurately measure, we're able to release a light beam, a laser, and time it until it hits another spot, a certain amount of time, and say that's 1 meter. Mass, it's a similar sort of story. It was very vague, and then it got a lot better. It was originally based off of how much water is kept in a jar at a specific temperature. And so that was just good enough for the time. That was a kilogram, just 1 kilogram of water. But you see, it's very vague. It can change just a little bit from case to case. So the same sort of thing happened about the late 1800s. They wanted to standardize it a bit more. So they made this cylinder, this sort of mass, that is kept in a jar, that's vacuum sealed, and is in a vault in every country. This mass is going to always be exactly 1 kilogram. That's sort of, we could do a little bit better than that now. And so now we're using, this is very recent, 2019. So now we're based off of, just some high level physics concepts, like how light and energy behaves. We are able to dictate or figure out what 1 kilogram is. This is all just history. I'm going to get to actual problems in a bit. And finally, we have time. So the unit of time is a second. It sort of is a nice and easy unit to have. It's just a fraction of the Earth day. So how many seconds are in 1 day? Can anyone do that on their top of their head? I can't. So it's 60 seconds in a minute, 60 minutes in an hour, and there are 24 hours in 1 Earth day. But now that we're able to actually measure things a lot better, we noticed the Earth day is getting longer every year. Earth is, it's spinning in space. It's slowing down. So we can't really accurately use that anymore. So we said, okay, ditch that idea. We're going to go to the year. The second was then, okay, just a part of the year divided out into fractions. I don't want to figure out how many seconds are in a year. But again, we figured out with better measurements, our years are getting longer. Not like drastic. It's like minuscule amount. But these changes, a longer day, a longer year, all of this has to deal with, we have to account for this somehow. And it was, I don't remember when, but the church created the calendar that first introduced leap years. And so it's every leap year, there's one additional day in the year, sort of to account for the Earth slowing down or being a bit longer. It's not exactly 24 hours in a day. So you can see, now that we're at a level of high technology measurement, we can base it off of, just specific things off of atoms. So here's a cesium atom that vibrates at a specific frequency, always. Very, very low amount of error when measuring this. So this thing, as we know it currently, will always be oscillating at a certain amount. And we're able to count, so, okay, when it oscillates, I'm just making a number, 50 times, that's exactly 1 second. So as time progresses, so do our units. We have to constantly update them, but that's just so we can all agree on the same value for our measurements. Before I move on, I want to bring up just a little story. There was once, I think it was in like 2004, a company was working for NASA to make a robot to go to Mars, sort of a rover type. And everyone's working together. NASA hires specific different companies to make specific parts. And they launch the thing. It's out into space and it's going. And NASA sees the rocket's not going, or the rover, it's getting close to Mars, but it's not going quite where they want it to go. And they're saying, why is that happening? Like we doing all of this, double, triple checking. Why is this happening? It's not doing what we want. They follow the trail of crumbs to this one company, and NASA always uses SI units. This company was using the imperial units, inches and feet. And so this rover actually crashed into Mars and was destroyed. If you guys ever make a rover, make sure you're using the same units as everyone else. Okay, this is where it's going to get hard for me. I have a table of, you don't have to write all of these down. It's in a book somewhere. You don't have to write all this down. I'd say maybe you could write the key ones. I'd say centi, so 10 to the minus 2. You write milli, and then over on the right, you write kilo. So those are the key ones you'll be doing in this class. And that's just so we can, refresh on what these mean. So, for example, if I have 1 meter how many centimeters is that? So there are going to be 100 centimeters in 1 meter. So how am I doing this? So a way I kind of, you picture it in my head, I'm taking the value, the number, the exponent, negative 2, and I'm saying, okay, we have a meter that is going to be larger than centimeters. So since it's larger, we're going to move the decimal point over twice, or centimeters. What if I'm going to do a similar sort of thing, 1 kilometer. That is how many meters? It's pretty much just the same type of problem. This is going to be larger than the meters. So there's going to be like a lot of meters in 1 kilometer. So there's going to be 1,000. Does it say 1,000? No. So I'm going to write. So So 1 kilometer is just 1,000 meters. All right. Yeah, a lot of these other ones I don't think I've ever used, like a femtometer. These are just prefixes you could put on any SI unit. So meters, liters, grams. I don't think you typically use them on seconds, unless it's like a nanosecond. That's the most common one. Yeah. Okay, here's the big example that I will do on the board. And for anybody like going to watch this later, I will take a picture of this work that I do. "90 kilometers per hour. And we want to figure out, I'll do it here. 90 kilometers per hour. And we want to figure out how fast is that in meters per second. Kilometers per hour. And we want to figure out meters per second. So we have, it's sort of phrased like this. The units are bundled together. I could have put it like that, show you that those are just units. You don't have to multiply these. I could also rewrite this to maybe make it a bit more clear. So that is 90 kilometers in 1 hour. So those two, ways I'm writing it is the exact same thing. Maybe that will make it a bit easier to make this unit conversion. I need to put up on the board what's, okay, there it is. I don't know on the top of my head what. There is 1.609 kilometers in 1 mile. So that's something we will need. I will also put how many seconds are in an hour. So we have 1 hour. Make it look like an H. So that's going to be 60 minutes. 60 again, that's 3,600 seconds. And yeah, last thing we can maybe use is 1,000 meters in 1 kilometer. So, I would probably have to look this up on my own, but that's easy. Once I have that, the problem is easy from that. So I take what I have on one side. Let's put it over here on this side. Where did I put it? 90 kilometers in 1 hour. I'm going to put that on one side. And we're going to put on the other side what we are wanting to find. Right. That will be meters. So this is me just putting the units of the arrangement that I want to find it in. Okay. And what I'll have to do is turn this numerator, it's close. I'll just have to turn that into meters. I'll have to turn the hours into seconds. Okay, so there are 1,000 meters in 1 kilometer. Let's do this one first. Let's say times, make a big parentheses. I don't want kilometers, I want meters. So how do I get rid of this unit? I will take the value with this unit and put it on the bottom. So there's 1 kilometer in 1,000 meters. So there are 1,000 meters in 1 kilometer. Trying to keep it light, keep it out of the way of everybody. So if we look at just units, we can cancel some things, see what's remaining. Cancel the kilometers. So there, one's on the top, the numerator and denominator. And so we can just do this, get this value. I just want to do the next one right away, so I don't take too much time if people already understand this. Move this over. Next up, we have hours. We need to turn into seconds, so I want to cancel this unit out. So I'll put 1 hour on the top. And how many hours or how many seconds are in 1 hour? 3,600. I wish I had red. Okay, so I can cancel the unit of hours. So what will be left, once I do this, I multiply everything on the top straight over, multiply everything on the denominator straight over, and it's going to be like a big number over a big number, and divide, I will get 25 meters per second. So I can write like this, 25 meters in 1 second. You write like that. However, whatever makes sense for you. Okay, going to miles. So we have 90 kilometers. Start with what we know already. And we're going to turn it into what we want, miles per hour. So there's hours already on the denominator. We don't have to do anything to that. We do have to turn the kilometers into miles. That is this conversion rate right here. And so we want to cancel the kilometers out. So we say go like that. This is kind of why I didn't want to write on the board, because it's like over here, that one gets dark because they haven't fixed the light. It's a big mess. Once you do this, those units cancel. We're left with just miles over hour. Miles over an hour. And that is 56. Put this over here. And so you're thinking, why are we even messing with miles per hour in the class? Once I gave that rocket, the rover story, it's because we live in the U.S. We're going to have to deal with it. We're going to have to make conversions like this all the time because we haven't switched over to the metric system yet. So we have our two answers. And that's awesome. Take a picture. Okay. Any questions on this? Yeah.
So when it comes to like rounding, do you round to like the significant figures, or do you want it to round to the whole year's whole number, or what?
In this case, or in like a problem that you're doing, you just look at the question at how it's asking you, and you see what the significant figures of the values they give you, and you use the lowest one. So in this case, it's technically one significant figure. I'm going to actually talk about significant figures right now. So this would actually be 30, and that would actually be 60. But this is fine. Significant figures. So I've talked about doing these conversions from one type to another. How many digits can we trust once we're taking a measurement? Maybe we're using the right ruler, but where do we actually mark the value? How many numbers do we get? How many numbers can we trust? So when you're recording a known value, so let me actually bring that up. When you're recording a value of measurement, what you're going to always do is write down exactly what you see first. So what is the length of this pencil right here that you see? Before you guess, what is it for sure? 5.6, and then you have to guess on that last digit, right? So the dotted line goes somewhere in between, and there's no real divisions for us to get a right value. That's the one that we're going to guess on, and that will be the last or the only one that will guess. We're not just gonna 5.6, 5, 1, 3. I can't guess. I can't just keep guessing at what the value is. So for that pencil right here, yeah, so 5.6, 5, maybe. All right, some rules to follow for significant figures. I was going to fill this whole slide. Let me put them over here. That's okay. So for significant figures, if it doesn't have a decimal point, you just count what you see. So this will be 2 significant figures, right? 2. Let's say it has a decimal point in it. 2, 5 point. Ooh. Now how many significant figures? Nice notation. So this will be all trailing zeros. If there is a decimal point, do count. So that sucks. That was the one I had. Okay. So if there is a decimal point, trailing zeros, do count. So this is like if someone gives you a value, you didn't measure it yourself. You're trying to figure out what number maybe they guessed on. You know, did they actually get this 5? Or maybe they have like a really long number? What to trust? So if there is a that 205. This will be 3 significant figures because if there's a 0 within 2 other values, it also counts. What did I say? 2, 3, 3. What if it's a very small number? What if it's something like actually before it goes small, let's go really big. What if it's like that? The one thing to look out for, there's no decimal point. There's no decimal. do not count. So this will be only two significant figures. This is like, how do I know someone actually measured that there are 25,000 grains of salt in this container? Did they actually measure? They got 0, 0, 0 exactly. This is where we kind of say we're only going to trust those first few. But remember, this rule counts. If they do put a decimal point, then that means that, oh, they actually did somehow measure all of those zeros exactly. Now let's go really small. So if there are leading zeros and there is a decimal point, leading zeros don't count. There's only two. That's two significant figures. Let's say leading zeros do not count. And the last one is sort of a trick one. Let's do it like make it real complex. Or no. I'm trying to show the rule. I don't want to make it too complex. So just something like this. This one, how many significant figures do you think?
Is it 3?
This one is 3, yeah. Because all the other rules still also apply. Leading zeros, don't care about them. Get rid of that. Doesn't start until right here. But there is a decimal point, and there are trailing zeros, so the trailing zeros do count. So this is kind of like the practice one. There we go. So this is going to be 3 significant figures right here. Okay, so significant figures come into play when you're trying to make something precisely or take some very accurate data, or like a homework or something like that. I believe it's like as you were asking the question earlier, you would usually go off of the lowest amount of significant figures in the problem already. So, like the problem earlier, it was just 90. So now you kind of see the rule of what I was saying. This is only one significant figure. And so my result, my answer right here, should also be one significant figure. So if I was to put this in, and the problem says be specific, significant figures. Okay, so one significant figure, the rest are not significant, so this should actually be 30 meters per second. This one, it's also only one, even though I'm using this, that's a lot of significant figures. The 90 right here, that's a very rough number. I have to always keep that the same. So this would be like 60. if I was to, be completely true with significant figures. Okay, yeah.
In homeworks and like quizzes and tests and stuff, would you want us to have it like in the corresponding for the significant figures, or?
For like a quiz or a homework or a test or something, I'd say I wouldn't like be severe unless the problem is significant figures. So unless I'm exactly testing to see what you know about significant figures, I'm not, if you're just like close, my mind is going to be on like other parts of the problem. If you get everything right and then you just don't happen to write it exactly, I can look away for that. But it's case by case. It depends on what the problem's saying. Okay. Scientific notation. Let me take a picture of this. Okay. So we're going to be recording a lot of values, writing them down, doing problems, this and that. What if I get a value like this, and I have to just keep doing the problem with this value? That will be very annoying if I had to always use that over and over and over, keep putting it in my calculator. It's a big hassle to have to deal with. Does everyone have this? Okay. So, develop scientific notation that probably sure you guys know already. Just want to make sure I go over it. And this is the first chapter. So if you already got all this, you're going to do great on the homework. And it's already like half of the next quiz. So I'd say it's good always to refresh. What if a value's huge? 75 million. You got to keep putting that in your calculator over and over and over and over again. First off, how many significant figures are in this? 2. So we're going to put 2 significant figures in the scientific notation. So we're just basically taking this value and condensing it and showing it as, so this will be 7.5, only 2 significant figures, so 1, 2, times 10 to a certain exponent. So what will that exponent be in this case? You guys are already on it. 6. So what I'm pretty much doing is I'm moving the decimal points so that it looks like this. So 1, 2, 3, 4, 5, 6, 7. So I had to move it over 7 spots. Why is it not 6? It's because it's not this right here. So this is technically, this is the same as this. But you see, there's no, I suppose you could write it like this. But, that's kind of getting you guys to think about it. What if it's a very small value? This is a bit more easy to see since the decimal point will already be in here. and I want to express this in scientific notation. Again, the reason I'm using it is because this is a hassle. Making sure that you always do it correctly every time. There are technically 3 significant figures in this one. So I will write it like 7.50 times 10 to a specific exponent. -5. So let's see. So 1, 2, 3, 4, 5. Yep. To the -5. Awesome. When we multiply scientific notation, we may be doing this on homework. We're going to be adding the exponent. So let's say, let's say that we have 2 values that we're going to multiply. I don't know, something like 3.0 10 to the second. I'm going to multiply that by 4.0. It's 10 to the third. Just something I made up. So what you're going to do there is you're going to add the exponents. So in this case that I've done, doesn't mean you add everything. I'm still multiplying the value in front. So this is going to be 12. But we're adding the exponents right here. So that's going to be 10 to the 5th. If we are going to be dividing with scientific notation, that's just subtracting the exponents. Like, very straightforward. We have example like, what are the values I used? Was it 8 and 2? No, 16, 2. Divided by something like 2.0 times 10 to the third. This result is going to be still doing the operation for the value out front, but I am subtracting the exponent. So this is going to be 8.0 times 10 to the what? Times 10 to the first, or just times 10. That's the same thing. Anything to the first power is just itself. So since it is just times 10, I can say that is also just like 80. So that's, beside the point. Now there's a problem. Yeah.
So the problem on the left, 12.0 is 3 6/8. So in situations like that, would you have us put the extra 0 at the end, or just do 12?
Oh, I said. Oh, 1, 2, 1, 2. Yeah. I suppose that is right. This would just be 12. And we can just put like a decimal point.
Right.
So when we are adding exponents, we can maybe get in a little trouble if we're a little careless. We sort of ignore the exponents. We have yeah. So say we just want to add exponents. Very easy to go too quickly. If you're not paying attention, you could mistakenly say this is 9.0 to whatever, the 10th power. Or, you're just sort of rushing through it. You're not paying attention to what's actually happening in here or what these values are. This value right here is 8,000. This value right here, 0. So that is what we're actually adding in this problem. So it's just sort of a thing to look out for. And the last part on scientific notation is when you raise a power to another power, the value is multiplied. So just like 10 to, I don't know, third, and we want to square that. That'll be 10 to the 6th. All right. That is all the scientific notation. Okay. Let's see. Yeah, I got time. I will go over some sort of coordinate systems because we're going to have to be taking some values, and eventually we're getting into vectors, which are, it depends on their direction and shape and size. So I had a grid plan, but that's out of the plan for today. So what are some coordinate systems? First, I'm going to talk about Cartesian coordinates or rectangular coordinates. So and what was I going to do? I was going to make a graph. It was going to look great. And I will try to make a graph over here. Yeah. Okay. I'm just going to put some random points on the graph. So let's say there's a point right here, point over here. So Cartesian rectangular coordinates is just sort of like left, right, up, down. It's very simple. Next to the point is typically where we'll put the coordinates for the point. So that one's kind of in between. And then coordinates for this one right here is going to be how far it goes, left, right. Goes positive 2, and then it goes up 4. All right. What are the coordinates for that other one? Going to be, yeah. That was 1, 2, 3, 4, 5. 1 and 3. Right. We're kind of limited when we're just using these coordinates, though, since the world, natural world, everything, it's not, rigid left, right, up, down. There are things that, you're not always going to have a perfect grid to measure left, right, up. It's exactly at this point right here. So even if I was to draw a line from the origin right here being 0, 0, there is still a little bit of it's good in that it's straightforward, but it's not always occurring in the real world. So what actually? Let's step back from this. Let me draw the rest of this triangle. We have the base that is a length of 5. I don't have any units on this graph. That's the first thing wrong with it. And it has a height of 3. How can we find the length of this hypotenuse right here? I think I've heard it. We're going to use Pythagorean theorem. And this is the one that just says a squared plus b squared equals c squared. Where a and b are the length and height of the triangle. So this would be like a equals that, b equals that, and c would be the hypotenuse. So just to find the hypotenuse, typically in books and everywhere else, they're too lazy to write this down. This version, they just jump straight to so that is what we use to find that side of the triangle. From that point on, that's where we kind of depart with just using the Cartesian coordinates. Everywhere else, we're going to use just a little bit extra. We're going to use some of polar coordinates. That's I have a different graph up. Let me put that one over here. That's going to keep erasing all the time. Okay. So for polar coordinates, I'm just going to have this grid, this sort of axis like this. Whereas on a typical axis, this I should have put. I have x and y. I can also find x and y values on a polar grid. So but it's helpful in a different way. So we're always going to start from the origin in polar coordinates. So we're always going to start here. Whereas, problem on rectangular, we can start one place and go to another. It's just like counting over there. This one, we're always going to start at the origin. And I'm going to say right here is 0. We're measuring like an angle sweep. So this is 0 degrees. Or if we wanted to use radians, it's just 0. Probably seen this before. Up here is pi over 2. Up here's pi. Down here is 3 pi over 2. Now, for this coordinate system, we can find values that just randomly out in space. And we don't have to get a grid paper. We don't have to measure left and then right. We could just say, I want to find that point right there. Okay? It's going to be that far away. And I only need to know the angle. And that is theta. It's a Greek letter theta for the angle. And the distance from the origin to this point is typically referred to as just r, or radius. Imagine if this thing were to sweep around, it'd make a circle, it'd make a radius of a circle. So we have this point out in space, make it actually connect in polar coordinates, is this. But how is this helpful to us? Well, it's easy to measure an angle. You're out in a field somewhere. You can measure an angle difference between two things. It's very easy to do. All you need is a protractor. That's this big. But there comes a time where we would also like, maybe we want to use this, but we also want to know how far left and how far left, right, and up, down it is. Those x and y coordinates that we found earlier. X and y. So how do we actually find those? X, what does that equal? What does that equal? This is where we're going to start thinking back to our trigonometry class. Think of a rule that we used that dealt with sides of a triangle and an angle. That rule, or at least a phrase that I always remember from my trigonometry class is SOHCAHTOA. If you haven't learned that, then I don't know. That's pretty much all of trigonometry that I remember. What this is saying is that sine of an angle, of a triangle, is equal to, so sine of theta is equal to, so just any angle of a triangle is equal to opposite over hypotenuse. opposites yeah. And we can just go to the other terms. This middle part is cosine is adjacent. So A is adjacent. This is adjacent side of the triangle. Adjacent over hypotenuse. And lastly, TOA is tangent. The angle is opposite over adjacent. So I think maybe I went, I'm not saying like the side, like going step by step. So opposite side of the triangle. So wherever the angle you're measuring, the opposite side will be this side. The adjacent side to the angle is this right here. And that is always the hypotenuse. Okay. Does everyone kind of remember that? From, yeah, cool. Okay, I think I'll finish up. Let me put just, actually no, I'll what time is it? Yeah, I think I'll start here next time. Hopefully I can get my thing to work. It'll be a lot better. It's going back and forth all today. So make sure you guys got the homework platform. If you have any problems, let me know. Yeah, I'll see you guys later then.